Well, here I'm showing you our Henderson-Hasselbalch equation, which is based on our most important physiologically important buffer system in the blood, I should say, physiologically important, the bicarbonate buffer system. When you are working with a buffer and you want to calculate pH, you always put the base on top in the numerator, which is our bicarbonate. The acid goes in the denominator, which is our CO2. What does pKa mean? pKa is the dissociation constant. Let's say you had bicarbonate and carbon dioxide and you put them in a container. It doesn't matter how much you have. I just want you to think that we are putting some in a container in a one-to-one fashion. For every CO2 you have a bicarbonate. If you could put in a pH meter into this container, your pH meter would detect a pH of 6.1. So let's explain why. First of all, I need to explain what this value of 0.03 is. The Henderson-Hasselbalch equation for our buffer system, as shown up here, is the pH equals pKa, which is 6.1, which I'll explain in a little bit, plus the log of bicarbonate divided by the amount of CO2, which is multiplied by this number, 0.03. What is this 0.03? Well, the unit for CO2 is in millimeters of mercury. This partial pressure, or PCO2, stands for partial pressure of carbon dioxide. It is a gas dissolved in your blood plasma. It exerts a pressure. It is measured in millimeters of mercury. Bicarbonate values are in milliequivalents per liter. The typical normal number is about 24 milliequivalents per liter. Well, my 5th grade math tells me that I cannot divide milliequivalents per liter by a different unit, millimeters of mercury. You cannot divide apples into oranges. So I have to convert one of these units into the other, right? I need to do that conversion before I can divide. pH is unitless, so I can't have any remaining units. They need to cancel out. The 0.03 is a way to convert the millimeters of mercury of CO2 into milliequivalents per liter. As I said, let's pretend we have a container and we have equal amounts of CO2 and bicarbonate. After we do our little conversion, if we have equal amounts, then let's say we have 1, as in 1 molecule bicarbonate, divided by 1 molecule of CO2. 1 divided by 1 is 1. If we were to take the log of 1 as shown in this equation, you would get 0. That means the end result in the equation leaves the pKa, which is 6.1. That is what our pH meter would detect if we had equal amounts of bicarbonate and CO2. Now, the question is, in our body, do we have equal amounts of bicarbonate and CO2? Well, let's see. Our normal value for bicarbonate is 24 milliequivalents per liter. Our normal value for CO2 is 40 millimeters of mercury. When I multiply my 40 millimeters of mercury by my conversion unit, 0.03, I get 1.2. If I divide 24 by 1.2, I get a ratio of 20. Now, I will remind you that we can take the log of 20. The log of 20 is the same as saying the log of 2 times 10. 10 to the power of what? 10 to the power of 1. So I can use the distributive property, like I showed you earlier, and take the log of 2. And do you remember what that number was? The log of 2 is 0.3. The log of 10 to the 1 is simply 1. So the log of 20 is 1.3. If I take my 1.3 and add it to my 6.1 pKa, my dissociation constant for this buffer system, I get 7.40. It is important to realize that our bicarbonate and our CO2 are not equal. They are not in a 1-to-1 ratio. Instead, the ratio is more like 20 to 1. We have 20 molecules of bicarbonate for every CO2 molecule we have. Because of that ratio, that number 20, when we take the log of it, we get 1.3. We add that to our pKa and we get our normal body pH of 7.40. That ratio of 20 to 1 is important. It reflects a base to acid ratio. We have 20 molecules of base for every 1 molecule of acid. That means we have really good neutralization power, a way to neutralize these acids as they are being made. They are being outmatched. Up at the top of this slide, you are seeing changes in pH, and you are seeing your bicarbonate in your numerator and the CO2 in the denominator. I've basically removed the pKa and the log function. Look, when you're determining your patient's pH and their pH imbalance issues, if you are working for a hospital that says, we want you to calculate exactly their pH, you should quit, because you don't need to do the entire Henderson-Hasselbalch equation. You can actually just reduce it to pH equals bicarbonate divided by CO2. You really can. Let me explain to you why. First, your job is to always remember that normal pH is 7.40. Your job is to always remember that anything lower than that is acidosis, and anything higher is alkalosis. Your next job is to always remember that the normal values for bicarbonate are 22 to 26 milliequivalents per liter. Your job is to also always remember that the normal values for CO2 are 35 to 45 millimeters of mercury. Look up at the top of the screen where I am showing you letters A, B, C, and D. You will notice that I have arrows next to the pH. Okay, how are we going to apply all of those bullets where I said this is your job to know this and this and this? If you hear me saying that pH is up from what? What does that mean? It means up from normal. So that means a higher number, right? What state is that? Well, I said on my bullets, anything high is alkalosis. So if your patient's body pH comes back and the pH is higher than normal, you should be thinking alkalosis, and let the diagnostic dilemma begin. Now you get to figure out why and what is happening. If you see that their pH is lower than normal, lower than what? It means lower than 7.40. That means acidosis. Next, you need to look at their blood values for bicarbonate and CO2. They will always be given. These are always measured in arterial blood gases. We call them ABGs. Now, how can a person have acidosis? Too much acid or too little base. How can a person have alkalosis? Too much base or too little acid. Look at part A. I am saying here, pH is up. What does that mean? Alkalosis. You're noticing that the bicarbonate is the problem. See the little P next to it? You are seeing that it is elevated. A person can have alkalosis from too much bicarbonate. Now, what does up mean? It means up from normal. That means more than 26 milliequivalents per liter. Why is the patient's CO2 value also higher than normal? Well, that is showing compensation. Now, you might be thinking, now, Kara, I am seeing pH is up, and I am seeing bicarbonate is up, and I am seeing that CO2 is up. And how am I to know that the bicarbonate is the problem and not the CO2? Stop and think. If the person has high CO2 and that was the problem, would they have high pH? Can you have a high pH because you have too much acid? No, that doesn't fit. So I will remind you that when the pH is a shift in one direction, the body will try and compensate by shifting the other direction. If you go back to slide 11, where I was talking about left shift and right shift, if a patient has high pH alkalosis because they are shifting to the left and making too much bicarbonate, then the compensation will be trying to shift to the right by making more CO2. In letter B, you are seeing a pH that is too low. That is acidosis, right? How can you have acidosis? Too much acid or too little base? In part B, you are seeing that both the base and the acid are low. So how can you have a pH that is too low? You can either have too much acid or too little base. In this case, the too little base makes sense. That fits your diagnosis of acidosis. The too little CO2 is the compensation. And I'm going to talk about how the body compensates in just a bit. In part C, you are seeing low pH, lower than normal. And how can we have that? Too much acid or too little base? In this case, you are seeing that both the base and the acid are up. Only one can be the problem. Only one fits the diagnosis. Too much acid. That means the increase in bicarbonate is reflecting compensation. Lastly, you are seeing a problem where I am saying that the patient's pH is too high. Again, how can you have that problem with alkalosis? Too much base or too little acid? In this case, both are low. They are lower than normal. Only one of those scenarios, however, fits the diagnosis and can be the initial problem. In this case, it is going to be the too little acid. The bicarbonate that is being released by the kidneys and excreted from the body is reflecting compensation. Now this is going to take more practice, and I am going to go through some examples. Let's put some of this together in one little handy-dandy slide. Mechanisms of acidosis and alkalosis. When we are playing with acid-base imbalance, we really can take this big Henderson-Hasselbalch equation and reduce it down to pH equals bicarb divided by carbon dioxide. You need to remember that acidosis is a pH lower than 7.40 and alkalosis is a pH higher than 7.40. Again, I am using 7.40 as my strict line here for normal pH. How can a person have acidosis? I am showing you this in red. It can be from too little base or too much acid, too little bicarbonate or too much CO2. Anytime the bicarbonate is the problem, we say the person has a metabolic disorder. Anytime CO2 is the problem, we say that the person has a respiratory disorder. How can a person have alkalosis, a pH higher than 7.40? They can have too much base or too little acid. So if a person has metabolic alkalosis, you are saying that their pH is high and it is due to a base problem, the bicarbonate. If you say a patient has respiratory alkalosis, you are saying that they have an elevated pH and too little CO2. Let's practice. Let's say we calculate that a patient's blood pH is too low. What is the problem? Is that alkalosis or acidosis? Did you say acidosis? Then that is correct. Good. Now step 2 is to determine what type of acidosis your patient has. Do they have respiratory or metabolic acidosis? In order to solve this problem, we would need to look at the patient's partial pressures of carbon dioxide and their milliequivalents of bicarbonate. Hey, I don't even have to give you numbers for this. Look at the screen. If I tell you that carbon dioxide levels are elevated and bicarbonate levels are elevated, we already determined in step 1 that the patient has acidosis. What are the two ways a patient can have acidosis? Too much acid or too little base. So which one of these problems is the problem? Look at the middle of the screen. Our patient already has too much acid and too much base. So which of these solutes was the problem? Did you say elevated carbon dioxide? You are right. Too much acid is one of the two ways we can have acidosis. Because it's the carbon dioxide that is the problem, the patient has respiratory acidosis. Step 3. What is the compensation and which is the organ system that can compensate? How do you know the patient is compensating already? Well, if it's a respiratory problem, then only the kidneys are going to be able to help the situation. What would they do? How would the kidneys rescue an acidosis problem? Did you say make more bicarbonate? Then that is true. How do you know if the patient is compensating already? Didn't I say that the bicarbonate levels were elevated in this patient? Then this reflects that they are compensating already. It is a good general rule of thumb to know that when it is a respiratory disorder, only the kidneys can compensate. But if it is a metabolic disorder, the lungs and kidneys can compensate. Let's try another problem. Here we have a patient that has elevated blood pH. What does that mean? Did you say that they have alkalosis? You are right. What are the two ways that a patient can have alkalosis? Too much base or too little acid. Let's look at the patient values. They have too little carbon dioxide and too little bicarbonate. Which was the problem? How can the patient have alkalosis? Too little acid or too much base? Are you seeing that the problem in this patient is that they have too little acid? If so, then you quickly realize that this patient has respiratory alkalosis. Perhaps the patient is compensating for this already. How do you know, and which organ system can compensate? Again, it is a respiratory problem, so only the kidneys can compensate. What would they do? The patient has alkalosis. Now would be a good time to get rid of the bicarbonate, the base, from the system. What would the kidneys do? They would not be able to reabsorb the bicarbonate that was filtered through the glomerulus. They would not have enough acid to titrate all the bicarbonate that was filtered. Therefore, some of the bicarbonate would not be reabsorbed and it would stay in the lumen of the nephron. This means that bicarbonate levels would elevate in the urine. This means that bicarbonate levels would decrease in the blood plasma. So yes, this patient is compensating because we can see that their bicarbonate levels are low. Let's do another one. Here I am to tell you that this patient's pH levels are too low. What does that mean? Did you say that they have acidosis? You are correct. Now our patient levels for carbon dioxide are too low, and our patient levels for bicarbonate are also too low. Which of these solutes is the problem, and which of these solutes reflects the compensation? Let's review again. How can a person have acidosis? The answer is too much acid or too little base. The patient has too little acid and too little base. Which of the solutes is the problem? You cannot have acidosis from too little acid. That is not possible. So clearly the problem is the lowered amounts of bicarbonate, not enough base. Perhaps the patient is compensating. Are they? How do you know? Well, which system can compensate for a metabolic problem? Well, did you say both systems? This is metabolic acidosis because it is now too little bicarbonate levels. How can the patient compensate? Both the lungs and kidneys can compensate. Which of the two systems would be the fastest? The lungs. Is the patient compensating? What would the lungs be doing? Ventilation rate is going to go up. Ventilation depth would also go up. This means more carbon dioxide would be expelled from the patient. This means carbon dioxide levels in the blood plasma would go down. So yes, the patient does have metabolic acidosis, and yes, the patient is already compensating through increased ventilation and depth. This is reflected by the decrease in partial pressure of carbon dioxide within the patient's blood. Let's do another practice problem. Here we have a patient whose blood pH is elevated. Carbon dioxide levels are elevated and bicarbonate levels are elevated. You don't even need the numbers to work your way through these concepts. Start with step 1. If blood pH is elevated, then what condition does this patient have? Alkalosis. Step 2 is to determine which system has the problem. Is it respiratory or metabolic? Again, how do you do this? How can a patient have alkalosis? They either have too much base or too little acid. The patient has elevated carbon dioxide. Elevated acid. Obviously, this cannot be the problem. The patient also has elevated bicarbonate. Clearly, this was the initial problem. Since bicarbonate is the problem, this patient has metabolic alkalosis. Perhaps the patient is compensating already. Are they? How do you know? In metabolic alkalosis, both the kidneys and the lungs can compensate. Which of the two organ systems would be the fastest to start compensation? That's right, the lungs. changing the breathing rate and depth. How would they change? If the patient has alkalosis, they have too much base or too little acid. The medulla oblongata will change the respiratory rate and depth. The patient will be taking fewer breaths and more shallow breaths. Carbon dioxide levels will be trapped. If carbon dioxide is trapped in the body, then carbon dioxide levels in the plasma will go up. So, is the patient compensating? Yes, because we see the carbon dioxide levels are elevated in this patient. Earlier I told you how kidneys can control acids and bases. Bicarbonate is the base, and it is freely filtered and enters the nephron at Bowman's capsule. So it is freely filtered across the filtration membrane. Now, the kidneys have two choices with this filtered bicarbonate. They can reabsorb all the bicarbonate, say when you need to use it to neutralize excessive acids that your body is making, or they can not reabsorb all of it. They can reabsorb some or none. Maybe you have too much base in your body and you don't want to reabsorb it, but want to eliminate it from the body. It is important to understand that when a patient has an acid-base disorder, if and when their kidneys are compensating, their urine will reflect the problem the body has. For example, if you have a patient that has too many acids, they are in a state of acidosis. You will see that the urine will become more acidic than normal, reflecting compensation occurring at the kidney level. If you see that a patient has alkalosis, well then the kidneys will not reabsorb as much of the filtered bicarbonate and more will appear in the urine, and the urine will become more basic. Again, if and when the kidneys compensate, the urine will reflect the problem that the body has. In acidosis, the kidneys can actually secrete more hydrogen ions. So in acidosis, the kidneys will reabsorb all of the filtered bicarbonate, but they also can additionally secrete extra acid. They do this in the late distal convoluted tubule, using special cells called intercalated cells. These intercalated cells secrete hydrogen, but in order to do this, they make brand new bicarbonate in the process, which is perfect, right? If a patient is in acidosis, their kidneys not only will secrete hydrogen to get rid of it, but will also make more base in the process of secreting that hydrogen. Now, what about your urine? What is the normal pH of urine if you've been hearing me say that the urine, if and when the kidneys are compensating, will reflect the problem the body has? Normal urine pH is about 4 to 8. It is more acidic in the morning. Why is that? Well, when you have been sleeping all night long, your body has gone into the post-absorptive state. Do you remember that? That means you are using your fats as fuel because you don't have any more glucose, which is a really good thing because your body being in a post-absorptive state means that you will glucose spare, right? Glucose sparing. You are sparing it for your brain. Your brain is still very, very active when you are asleep. So it is a really good thing that your insulin-independent cells, your nervous tissue, have access to glucose while you are sleeping, and that your body insulin-dependent cells will shift while you are sleeping to fatty acid metabolism. These cells will use beta oxidation, and as a result, beta oxidation generates more acids. That means your morning urine will be even more acidic, reflecting your increased fat burning. And I put on our Blackboard site a short 3-minute YouTube video of Will Ferrell in Land of the Lost, who describes using hadrosaur urine as a method of camouflage. Enjoy.